Good morning, good afternoon, good evening. Thanks for watching the video. This is probably how we're going to do this for the next couple of weeks while we are social distancing, just so I can get you guys some of the material and that you don't fall behind. So thanks for watching the video. If you haven't already, please print out the note sheet. If you can't print, that's totally fine. You can start a notebook for Algebra 1, and that way, as the days go on, you can just fill in your notebook the examples, and you can have something to look back at as you're doing the assignments and you're submitting them. We're moving on to Chapter 8. Chapter 8 starts with an introduction to factoring quadratic expressions. We'll explain what that means as we go. So what we'll do is we'll do 8-1 right here on the note sheet. 8-2, there'll be a separate video where I do it on the computer just because I want to use some of the software that's available to us. So I'll do some screencastify video for 8-2. So let's start with 8-1. Review what you know about products and sums below. So for part A, write the area of the rectangle I write as a product and as a sum. Remember that the product represents the area found by multiplying the length by the width, while the sum is the result of adding the areas inside the rectangle. So you should take a second to pause the video and try to fill in this rectangle and write it as a product, which is multiplication, and write it as a sum, which is addition. So pause the video now and try it for yourself. All right, guys, so filling in some of the things that we know, just from what we can see right here, we know that these size rectangles are going to be y, so we can fill in a y for all these rectangles. It looks like all these are going to be y as well. It looks like right here we have an x rectangle, so this is going to be x as well. Notice these small ones are just 1 squares, so then we can put in little ones for all these guys. They are the same. And then notice that this is the same size as this for rectangles, so all these will have to be x's as well. All right. So that's how you fill in the rectangle. How about writing it as a product? Well, I would need to say, what is the length for this entire side over here? So I would also need to say, what is the length for this entire side here? So let's start with this side on this one. We know that here we have this length, and that matches up what this length is for this rectangle. So this is going to be size x. We know that this little piece right here is a size of 1, so that would be a size of 1. This would also be a little size of 1. This will be a size of 1, and this will be a size of 1. So altogether here I have x, and I've got 4 ones, so this would be x and this would be 4. If I want to get the entire side, I can add them together. So this entire side is going to be x plus 4. How about this other side over here? So over here, we'll start with this one. We know this is going to be size y, for the same as this rectangle. We have this one right here, which is size x. And then here we have size 1, and here another little size 1. So altogether we have y, we have x, we have 1, and we have 1, which is 2 1 tiles. So altogether we have y plus x plus 2. So if I want to find the area of a generic rectangle, I just do length times width. In this case, the length is x plus 4. The width is y plus x plus 2. So what you can say is, I'll take x plus 4. That's one of the sides. I'll put it next to, in parentheses, y plus x plus 2. When you put them next to each other, in math, this implies multiplication, so this would be the product. Now, if I want to write this as a sum, I just have to add up all the areas inside the rectangle. So I'll start with saying the biggest rectangle. So the biggest rectangle, or biggest piece inside of here that I can see is the xy. How many of them do I have? I just have 1, so I can do 1xy. The next biggest thing I see inside here is an x squared. How many of them do I have? Just 1. So then this will be plus 1x squared. Now the next biggest thing I can see are these y rectangles. If I look at them, I only have 4 of them, so I would say plus 4y. The next biggest ones are the x's. I have 4 there and I have 2 there for a total of 6, so that'll be plus 6x. And last but not least, I have 1, 2, 3, 4, 5, 6, 7, 8 1 tiles, so then this will be plus 8. Notice how, because I added them all together to get all of these inside of here, adding means that this is going to have to be the sum. All right, and I know that if I take these length and width and I multiply to get the area, that these two will be the same. So I can say that these are going to be equal. So our final answer would be like this: x plus 4 times y plus x plus 2. That's again x plus 4 times y plus x plus 2 on the outer dimensions. And if I do that, I get this sum. It's the sum of all the rectangles on the inside. All right. So if there are no questions there, move on to part B. Pause the video for a second and try it for yourself. It says, use a generic rectangle to multiply 6x minus 1 times 3x plus 2. Write your solution as a sum. You really should try to write it as a product and as a sum. I think that's just a good habit to get into. So pause the video and try it for yourself before I explain. All right, guys. So let's see what happens. I'm hoping that you drew a rectangle. So in this case, you draw a generic rectangle, a 2 by 2, because there are 2 terms in here and 2 terms in the second one as well. So for the first one, 6x minus 1. And then here I have 3x plus 2. So they gave it to me as a product because the 2 were being multiplied. So if I wanted, I could write it here, 6x minus 1 times 3x plus 2. I want to find out what this equal to. So in this case, I have a product. If I can find out what's going to fill in for these boxes here, then I can add them together. And when I add them together, that's going to be the sum, and that's going to be on this side here. So how do you fill in the boxes? Well, if you know the side lengths, we know that if I want to find the area, I need to do length times width. So in this case, 6x times 3x is 18x squared. Negative 1 times 3x is negative 3x. 6x times 2 is 12x. And negative 1 times 2 is negative 2. Now, if I want to write it as a sum, I need to try to combine as many of these things as I can. So the biggest term that I can see inside there is the 18x squared. The 18x squared can't combine with anything else, so it will go first as 18x squared. Along this diagonal, I see that I have 2x terms, which means I can add them together. Negative 3x plus 12x is the same thing as 12x plus negative 3x, which is the same thing as 12 minus 3x. So in this case, 12x minus 3x is 9x. And last but not least, the last thing I have inside of here is negative 2. There's nothing else that can combine with negative 2, so it's just negative 2 by itself, and this will be the sum. So in this case, I have the product equal to the sum. Nothing terribly new, but a good review, because it will tie into the introduction on factoring quadratics, which we're going to know. All right, guys, if you have any questions, feel free to shoot me an email. We can hang out on a Google Hangout, and I can explain it face-to-face if you'd like me to. I'd be more than happy to do that. As for 8.2 here on the bottom, we are going to skip that temporarily. There will be a second video that I post here for 8.2, where I use some virtual algebra tiles to try to explain how to do these. So watch the second video for 8-2. All right, let's move on, and then you can watch the other video for that one. So what do we have here? In 8-3, find the sum and the product of these generic rectangles. So very similar to the example that we just did a second ago, I'd like to do the same thing here. But notice here they give you the opposites. Instead of giving you the outside and asking you for the inside, in this case they've given you the inside and are asking for the sum and the product, which means you have to find the outside. So the easiest way to do this is to ask yourself what the boxes on the inside have in common. So if you want, pause the video. You can try it for yourself before I explain, or if you just want the explanation, feel free to let the video roll and listen to my explanation. So how about finding the outside dimensions? So if I wanted to find out what this dimension was for this rectangle here, I'd ask myself, what's the biggest number that 2x and 5 have in common? Otherwise known as, what is the greatest common factor of 2x and 5? Well, the biggest thing that 2x and 5 have in common is 1. Notice 2 can't go into 5. 5 doesn't have any x's, so the biggest thing that they both have in common is just a 1. Now, if I want to find out what's going to go here, I would have to go with these two boxes and say, well, what's the biggest thing that they have in common? Let's start with 6 and 15. So they do have 1 in common, but they also have 3 in common. And you might think 6, but 6 doesn't go nicely into 15. So in this case, the biggest thing that 6 and 15 have in common is 3. Now I'll look at the x's. This has an x squared, and this has an x to the first power. So what's the biggest that they have in common? An x to the first power. So in this case, the GCF of 6x squared and 15x is 3x. Since they're both positive, I can say this is the same thing as 1 plus 3x, which is also the same thing as 3x plus 1. Now, if I want to find out what's happening here on the bottom, I can do the same thing. I'll find the GCF of these two. What's the GCF of 2x and 6x squared? The biggest thing that 2 and 6 have in common is 2. The biggest thing that x and x squared have in common is just x to the first. So the GCF of those two is 2x. How about the GCF of 5 and 15x? The GCF is 5. I can't take any x's because this 5 doesn't have any x's. It is positive, so this would be 2x plus 5. Now that I have the outer dimensions and I have the inner dimensions, I can do the sum and the product. So we'll start with the product. If I take length and multiply by width, length I could say is 3x plus 1. I can multiply by the width, which is 2x plus 5. That will be the product. I'll set it equal to the sum. which means I need to add up all these things on the inside. The biggest thing that I can see inside of here is the 6x squared, so that will start off by itself. I do see along this diagonal that I have two x terms. They're just x to the first power, so I can combine them. 2x plus 15x is a 17x. And last but not least, I have a 5 there, which can't combine with anything else. So it'll just be a 5 by itself, and this will be the sum. So a final answer for this question would look something like this. 3x plus 1 times 2x plus 5 is the product, or the length times the width, and that's equal to 6x squared plus 17x plus 5, which is the sum of the inner areas. All right, guys. If you watched the first example and you want to try the second one for B and C, feel free to pause the video and you can try them on your own before I explain. Otherwise, here comes the explanation. In a very similar fashion, you'll start by finding the GCF of the squares that you have here. So here I have negative 2y and here I have negative 6. Then notice the negative 6 doesn't have any y's, so the GCF, or the biggest thing they have in common, is negative 2. How about here? I do see with 5x, y, and 15x that the biggest thing that 5 and 15 have in common is 5. Notice they both have a single x, so I can take that out as a GCF. I can't take any y's because this one has a y, but this one doesn't. So in this case, 5x minus 2 is going to be on this side, and it's 5x minus 2 because I took out a negative from the top as well. Alright, so how about going down this way? Well, here I have negative 2 and I have 5. They don't have anything in common besides 1. This one doesn't have any x's, so I can't take an x as a GCF, but they both share a y. So in this case, I could say 1y is going to be my GCF going down this way. How about between negative 6 and 15? The biggest thing that they have in common is 3. I can't take any x's because this negative 6 doesn't have any. So because here I have 1y and here I have 3, the biggest thing I can take out is positive, so I can make this a plus. So now I'm ready to write it as a product and as a sum. So if I write this one as a product, the product is going to be 5x minus 2. That's the length, multiplied by the width, which is y plus 3. That will be my product. Can I write it as a sum? I'll go back inside the box. What's the biggest thing that I can see in there? The biggest thing I can see is this 5xy. There's nothing else I can combine with it, so it's just 5xy. Along this diagonal, we normally are able to combine things, but could you combine a negative 2y and a 15x? No, they're not like terms, so I do have to just write them separately. I always write the x's first by habit, so I can say 15x minus 2y. Nothing else combines with this negative 6, so that will go there at the ends, and that will be the sum. So in that case, the final answer for this one would look something like 5x minus 2 times y plus 3, which is the length times the width, and that's equal to 5xy plus 15x minus 2y minus 6, which is everything inside of here. Nothing combines, so that's why everything is out on its own. Alright, how about C? Again, if you didn't get a chance to try it and you want to, feel free to pause the video. We'll go from there. Otherwise, let's jump in. So how about here? I can see that I have negative 9 and I have negative 12. The biggest thing that they have in common is negative 3. I can't take negative 6 because negative 6 doesn't go into negative 9. I can't take negative 9 because negative 9 doesn't go into negative 12. So I have negative 3, and it's negative because both of these are negative. Now notice both of these are positive, so the thing I'm going to take out is going to be positive. Now what's the biggest thing that 12 and 16 have in common? The GCF of 12 and 16 is 4. Why can't you take 6? Because 6 doesn't go into 16. And you can't take anything larger because 4 is the biggest thing that 12 and 16 have in common. Now notice here you have an x squared, here you have x to the first, so the biggest thing you can take in terms of x's that they have in common is x to the first power. So this side looks like 4x minus 3. Alright, how about going down this way? If I go down this way, the biggest thing that negative 9 and 12 have in common is 3. Notice this has an x to the first, this has an x squared, so I can take a single x as a GCF there. How about here? What's the GCF of 12 and 16? Well, that's also going to be 4, but I can't take any x's because 16 has an x and negative 12 does not. So in that case, it's positive, that's going to be plus 4. So here, for the length, I have 4x minus 3. For the width, I have 3x plus 4. So let's write it as a product and as a sum. So if I write this as a product, which I'll write down here so I have a little bit more space, I have 4x minus 3. This is like the length. I have 3x plus 4, which is like the width. And what I can do is, if that's the product, I can set it equal to the sum. Let's go find the sum. For the sum, I see what's the biggest thing inside of my rectangle. My biggest thing inside there is a 12x squared. Along this diagonal, it looks like I can combine. I have a negative 9x and a 16x. If I combine them, that is the same thing as 16x minus 9x. which is 7x. And then the last term I have inside of here is negative 12, which doesn't combine with anything else. So it'll be just negative 12, and that will be the sum. So in this case, the final answer for part C, 4x minus 3 times 3x plus 4 is equal to 12x squared plus 7x minus 12, which is the sum. We're adding up all the areas on the inside. Okay, so if you have any questions, like I said, you can shoot me an email or come see me in the Google Hangouts. Otherwise, let's finish this video up with 8-4, and then I'll make that second video so you can see 8-2. So let's take a look at 8-4. What does 8-4 say? While working on problem 8-3, Casey noticed a pattern with the diagonals of each generic rectangle. However, just before she shared her pattern with the rest of the class, she was called out of class. The drawing on her paper looked like the diagram below. Can you figure out what the two diagonals have in common? So maybe take a second to look at it. Here we have a 6x squared, and here we have a 5. Here we have a 2x, and here we have a 15x. So maybe take a second, pause the video, and see what you think. Can you find any things that these two diagonals have in common? One thing in common that a lot of people say is these two here are x terms, which we do see back in the problem 8-3 for A and for C. We were able to combine those. So that definitely is one pattern that some people see, is those two are like terms. You could combine them if you wanted to. Along this diagonal, you have a 6x squared and a 5, which you couldn't combine because they're not like terms. So that's one pattern that people notice. Another kind of a sneaky pattern is what would happen if you multiplied these two things. So what if I took a 6x squared, maybe I'll write it here. If I take a 6x squared along this diagonal and I multiply it by 5. If I take that and multiply it, well, 6 times 5 is 30, and then there's an x squared. So that would be a 30x squared. How about if I multiply on this side? Well, here I have a 2x. Now let's say I multiply it by 15x. 2 times 15 is 30, and then x times x is x squared. Remember, this is because x to the first times x to the first. You add the exponents and that'll become x squared. So another pattern that is actually common here is that if you multiply along the diagonals, you'll find out that it actually comes out to the same thing. 6x squared times 5 is 30x squared, and 2x times 15x is also 30x squared. So that's what the two diagonals have in common, and that's going to be something that shows up a lot in the upcoming lectures when we start talking a little bit more about factoring quadratic expressions. Alright guys, if you have any questions, feel free to shoot me an email or come see me in the Google Hangouts. Otherwise, there'll be a second video for 8-2. Please watch the other video as well. It is kind of important for where we're going. See if it makes sense, and then you can do the homework assignment. For the homework assignment, you can then do it on a separate sheet of paper and submit it as a picture or a PDF. Alright, I look forward to seeing you in the video for 8-2, where we start looking at this guy a little bit. We'll take some virtual algebra tiles and see if we can answer this question right here. Alright guys. Thanks, and see you in the second video. Bye!